Hello everyone. Welcome to week 8 of problem solving session. This week also we will try to solve various types of energy balance problems. Okay, so let's directly start with problem 1. Before that, quick introduction about myself. I'm a PhD scholar in the Department of Chemical Engineering, IIT Kanpur, and I'm working in the area of tissue engineering through the power printing. If you have any questions related to the course content, feel free to post your queries in the course discussion forum, or you can also reach out to me at my email. So, for the past 7 weeks, today is the 8th week, we have been doing this problem solving sessions from 3 to 5 p.m. on every Saturday. This will continue for four more weeks till 12th of April. The session recordings are all available in my YouTube channel. You guys can go and subscribe and you'll get notified about it. The notes used for these sessions are also made available to you guys in the NPTEL course platform. Feel free to check them out as well after the class. And let's begin. This is the first question. The question states that a gas containing 20% methane and 80% air by volume is to be heated from 20 degrees Celsius to 400 degrees Celsius. The flow rate of the gas is 1000 liter STP per minute. Please note this unit. Okay, it's a bit unique. And it is also mentioned that you have to take some reference dates. So these are 20 degrees Celsius 1 atm gas for methane and 25 degrees Celsius 1 atm gas for air, respectively. You have to calculate what? You have to calculate the required heat input in kilowatts. That is what we have to get. So let's quickly start by drawing a flow chart for this particular process. This is a heater, and this heater is used to heat a mixture of gas. Initially, the gas contains 20% methane and 80% air by volume. So methane is 20%, air is 80%. Since it is just being heated, the composition of gas will remain same after heating as well. So initially the temperature is 20 degrees Celsius, final temperature is 400 degrees Celsius. Same information will be added to this diagram as well. The flow rate of the gas is 1000 liter STM per minute. So STP per minute. So first, the basis will be your given flow rate. Also note the flow rate is given in STP, liter STP per minute. What does this mean? This does not imply that gas is at STP, means 0 degrees Celsius and 180. This does not imply that gas is actually at STP condition. But what this implies, this means that we are given the we are given the volumetric flow rate which has been converted to what it would be if the gas is at resting. Again, I'm repeating the volumetric flow rate value that we are given. This basically implies that we are given a converted value. We are not given the actual value, first of all. We are not given the actual flow rate of this gas mixture at 40 degrees Celsius. But what we are given the flow rate of the gas if it would have been at STP. So what this means, we have to convert it. We have to convert the flow rate to actual conditions. So how will we do that? We have to use ideal gas law. According to this, 1 mole of gas occupies 22.41 liter at STP. If we use this conversion, then we will get the actual volumetric flow rate. So here we will convert it to molar flow rate, mole per minute. We are given volumetric flow rate, we have to convert to molar flow rate. That will be 1000 liter STP per minute. Okay. 1 mole of gas occupies 22.414 liter STP. This will automatically give us the actual value. So we have to use this conversion. Note, we have to use this conversion factor to convert the volumetric flow rate, which is given as liter STP per minute, to molar flow rate, which is mole per minute. So if we do this division 1000 by 22.414, we should get 44.6. So I didn't do it now because I had already done it before. But you can pause the video and then you can solve it and check if it is right. So now if you write the energy balance equation, the general form is this. So in this particular process, delta Q is 0. Potential energy is also 0. Work is also 0. And there is no accumulation of energy. This means Q is equals to delta H into M, or Q is equals to delta H, or in terms of flow rate, is Q dot is equals to delta H dot. This means if we can find out the change in enthalpy, it can tell us what is the amount of heat required. Now we calculate change in enthalpy. Enthalpy out minus some enthalpy in. So there are two species involved. That's why we have to take their mole fractions in Ni, enthalpy of each component minus enthalpy of each component. This is how we get change in enthalpy. Now given we are given some reference states. The question for methane, it is gas 20 degrees Celsius 1 atm. Gas 20 degrees Celsius 1 atm. And for air, it is gas 25 degrees Celsius 1 atm. So when the reference states are given, we have to assume that enthalpy at this reference state is C. And you see, conveniently, we chose a temperature at the reference state of methane is 20 degrees Celsius. And the initial temperature of methane is of 20 degrees Celsius. So in our calculation, initially we can safely assume that at 20 degrees Celsius, the enthalpy of methane is zero. Okay. This is the information, important information. Now let's draw an important table. The table would look something like this. In, out, with other species, CH4 in air, under N number of moles, flow rate of these moles, given as mole per minute, and specific enthalpy in kilojoule per minute. And in out, similar quantities. We have CH4 and air as species. So in a temperature 20 degrees Celsius, and I told you that it is a reference state for methane. So here at N there will be 0. And enthalpy out for methane is unknown. So let's assume it as H hat 1. How we will determine the number of moles, not number of moles, the molar flow rate. So we will use 0.2 and 0.8, the percentages of gas, or percentage of each species in the gas mesh. In and out molar flow rate. Overall, we are given the overall. So you can calculate here only. Molar flow rate for CH4 will be 0.2 into 44.6. And for air, 0.8 into 44.6. This will come out to be, just give me a minute. So it will come out to be 8.93 mole per minute. Second one is 20 into 446. is 25.68. So that is what we have to write here as well. So in and out, therefore, it's the same level enthalpies being changed. For air, it is 35.68. So for air, enthalpy gain, we don't know yet. So let's consider this with the variable H2 hat. For air, out, enthalpy, we don't know yet. So with these two values, can get easily from your enthalpy tables. So if you go to B8, it is B8 table in the book Elementary Principles of Chemical Processes. So you can download the book, get it from the library. So you can find the complete name of the book. In this book, if you go to table 8, B8, sorry, which gives the specific enthalpy of selected gases in kilojoules per mole. And here we can see a point for the. Now what we need two information. First, at 20 degrees Celsius and at 400 degrees Celsius, the pressure is 1 atm. For species air. Is for the person. Go back. For 20 degrees Celsius, there is only 0 degrees Celsius and 25 degrees Celsius. There is no mention of 20 degrees Celsius. So we have to do linear interpolation. So if we do that, now the basic formula of linear interpolation is y is equals to y1 plus x minus x1 by x2 minus x1 into y2 minus y1. So here y1 will be minus 0.72 is the enthalpy at 0 degrees Celsius, plus x will be 20, x1 will be 0, x2 will be 25, and x1 is again 0 into Y2 is Y2. Y2 is 0 plus 0.72. If you solve this quickly, you should get the enthalpy value at 20 degrees Celsius. It should come to be plus. Allow me some time when I complete this calculation on my calculator. So I'm getting minus 0.153, which is exactly in kilojoule per mole. Now for 400 degrees Celsius, let's see is the value given or not. Yes, it's given. It's 11.24 kilojoule per. Now only unknown that is left is to think that only unknown that is left is H. So how do we calculate that? We can calculate it using its heat capacity equation. Okay. CpCH4. So how would we find the capacity equation? If we go to again the book Elementary Principles of Chemical Processes, in that book table P2, here you will see that heat capacities are given in equation form and the coefficient of that equations are given for for a large number of compounds. If you find methanol here, yes, there it is, methanol is given. It is given in two forms, liquid and gas form. So we don't need the liquid form, we only need the gas form here. So not methanol or methane. Sorry, confusion. Wait, for methane gas form in degrees Celsius, it is like this. This is the values. Okay. So how do we write this equation then? The form of the equation that we'll use is this form 1, A plus BT plus CT square plus D 3 cube. And we know the values of A, B, C, and D from the table. There we go. Well, let's copy these values. Okay, for methanol. Sorry, not for methanol, for methane. Cp is equals to 34.31. Now note, it is multiplied with 10 raised to the power 3, but we must write it as 10 raised to the power minus 3. You can see in the instruction on how to use this table, they have clearly mentioned with an example that let's say coefficient of B for acetone is 20.10, and it is multiplied by 10 to the power 5. But in example, they have shown that you have to multiply with 10 to the power minus 5. Similarly, to follow minus 1 point minus 12.78 into 10 to the power minus 8. Then 34.72, 10 to the power minus 12. So you have to follow the same convention when we write for methane as well. B is 5.469. 10 raised to the power minus 5 plus C, that is C, 0.3661 square minus 8 square minus 11 square 80. So this is your equation for Cp, specific heat capacity. And you know H is equals to Cp dt or H1 cap is equals to the integral from initial 20 to 400 final. Then we can get the value. Let's do the integration. You put the values now, then you should get the value of enthalpy to be 17.4 kilojoule per minute. You can verify this by solving the previous expression by pausing the video and doing it yourself. I got this value when I saw the problem myself before the class. Okay. This is the value of H1. Now we have all the values to get delta H dot, and then we can get Q dot. So let's rewrite it. If we see in out section, ethanol is going out. So you substitute the values for convenience. H1 we got 17.41. H2 we got minus 0.153. And H3 is 11.24. So we have to add these two, multiply these two, and then add this quantity with this quantity. Okay, similarly, we have to do for the other side as well. 8.93 into 17.41 plus 35.68 into 11.24. So the outside, so mole per minute into kilojoule per minute gives you kilojoule per minute minus in this first part will be 0, so no need to write. And this is the second part, 35.68 0.143. So you solve this. Again, allow me a few minutes to put this values in my calculator and get the answer. Should be 961,799. Now we were asked to get swing input in kilowatts. What is kilowatt? 1 kilowatt is 1 kilojoule per second. So basically now what we have to do, we have to convert this unit by just dividing with 60. So you should now get 9.36 kilowatt. This is your answer for this particular question. Any doubts? If you have any doubts, please feel free to reach out to me or please anything question. Post forward as well. Let's move on to the next question. For this question, I have given the table that we need already. Here you have to calculate the enthalpy change for 1 kg of nitrogen, which is heated at constant pressure, 1000 kilopascal, from 18 degrees Celsius to 1100 degrees Celsius. It's the table. This table is what we need. Here the gas that we need to work with is nitrogen. The nitrogen is heated from 18 degrees Celsius. Nitrogen is nitrogen, 18 degrees Celsius to 1100. This is 11. Okay. This is the table for mean heat capacity. From the mean heat capacities, we can easily calculate enthalpy change. So enthalpy change, change in enthalpy is basically enthalpy at final state 1100 degrees Celsius. Enthalpy at initial state 18 degrees Celsius. Now assume reference state is 0 degrees Celsius. The enthalpy at 1100 degrees Celsius would be this Cp value 31.593 into change in temperature is 1100 minus 0 minus Cp at 18 degrees Celsius is 29.12. Here 18 minus 0 degrees Celsius with respect to reference state. So it's easy. You have to calculate, multiply with this one, multiply with this one. Thirty-four 53.1 kilojoule per kg. This will be a change in enthalpy. That's something that it's the third question. Sorry. So So here what we have to do, we have to calculate change in enthalpy using in capacity equations. Conversion of solid waste to noxious gases can be accomplished in incinerators in an environmentally acceptable fashion. However, hot exhaust gases must be cooled or diluted with air. An economic feasibility study indicates that solid municipal waste can be burned to a gas of the following composition of gases. This is the composition of the gas. What is the enthalpy difference for this gas between the bottom and the top of the stack? The temperature at the bottom is 500 degrees Celsius and temperature at the top is 200 degrees Celsius. Ignore the water vapor in the gas. Because these are ideal gases, you can neglect any energy at the resulting maximum release. Gases can be so you have to determine delta H here. First, let's start with finding the heat capacity equations for each of the components that is given here. CO2, CO, O2, N2. Here's the table which we have to use. So first gas is CO2, carbon dioxide, so for CO2, values are degrees Celsius. So let's write it like we did in one of the previous problems. CO, CO is given here, carbon monoxide. For oxygen, Do we have for oxygen? Lastly, for N2, which is the values. So these are the equations. Now, what we have given individual percentages of the gas, right, in the question. So what we can do, we can multiply these percentage combinations with the 6 value and convert it. So this entire thing will be multiplied with 0.092 or CO2. For CO it is 0.015. For O2 it is 0.073. And for N2 it is 0.82. When you multiply it, you will get the final CP values. For CO2, CO, O2, and N2. I'll use my calculator for this. Now that we have calculated the final CP, what we can do, we can add this up and get net CP, which is something like this. This is the net CP value that you get. So now delta H hat will be the bottom of the stack is at 550 degrees Celsius, and temperature at the top is 200 degrees Celsius. We have do integration within this range for CPNet. If you do this integration, you should get net enthalpy of minus 11.3 kilojoule per. I understand this was a very long question, right? But I hope you have understood like how the calculations were done. These are pretty straightforward. I just took the the heat capacity equations for each of the components multiplied with the individual mole fractions of each of the components, added it up, and did integration. Get it changing enthalpy. So moving on with the next question. So you are given 150 gram mole per hour of liquid in hexane at 25 degrees Celsius and 7 bar pressure. Is vaporized and heated at 350 degrees Celsius. At constant pressure. Neglect the effect of pressure and enthalpy. Estimate the rate at which heat must be supplied. So, if you do a general energy balance, then you must have understood changing kinetic energy is zero, change in potential energy equals zero. There will be no work done. There is no accumulation of energy as well. Simply, we will have Q is equals to delta H or Q dot is equals to delta H dot. So if we will estimate delta H dot, then we will get Q dot. Okay. Now the NHC is in liquid state. Yeah, NHC initially is a liquid state at temperature 25 degrees Celsius, 7 bar pressure. Okay. And it has to go to final state, which is a vapor phase, which is at 350 degrees Celsius. And the pressure is constant, 7 bar. So in order to understand how from liquid to vapor the phase change is happening, we have to find out what like possible paths are there. So it's possible now if you the initial material, liquid and hexane, has to go to some state which is at a higher temperature than 25 degrees Celsius, and then it will convert to vapor phase. But whatever the state is, we should have information about this state. Otherwise, it will be very difficult to solve the problem. So if we look at the table of physical property, this table is again given in the same book, Elementary Principles of Chemical Processes, table B1. And for various compounds, they have given the heat of vaporization, boiling point, melting point, crystallization temperature, fusion temperature, heat of fusion, etc., heat of combustion. So various information is given. So in this particular table, if you go and find an hexane, there you go. So for N-hexane, you'll see So this sixth column is for the boiling point. Seventh column is for heat of vaporization. So N-hexane boils at 68.74, close to 69 degrees Celsius, with the heat of vaporization of 28.85. So we can take this particular state as our intermediate state here, whose information we already have. So N-hexane will convert the vapor at 68.74 degrees Celsius. What's the pressure? The heat of vaporization is given at QV and pressure 1 atm. So pressure is 1 atm. And this particular state where it is vaporizing, it at this state it will transit to a higher temperature at 3050 degrees Celsius and higher pressure 7 bar. So we can follow this particular path in order to get the net change in enthalpy. So here, let's say the change in enthalpy from state 1 to state 2 is delta H hat A. From state 2 to state 3 is delta hat HB. There will be two more states here. Think about, I just thought about it. First, in hexane liquid at 68.74 degrees Celsius, it will be liquid state 180. It will require some enthalpy to first go into vapor phase, which is here delta H P, heat of vaporization, to convert vapor phase, and from this vapor phase, N-hexane will completely convert to vapor in Celsius 7. This change in enthalpy, let's see, is delta H. So let's determine each of the values one by one: delta HA, delta HB, and delta HB. We will define each of them. Now, delta HA is equals to V hat into change into pressure, because we cannot neglect pressure now. This pressure is getting changed, right, from 1 bar to 7 bar to 1 8. We have to consider that term, as well as we are given some volume as well. So, C is G. continue. Here, the change in temperature is from 25 degrees Celsius to 68.74 degrees Celsius. Cp, here the state is in liquid state. So N-hexane, liquid, butane. This will come out later. Delta P here is 1 atm. 1 atm corresponds to 1.0131 bar. So 1.013 bar minus 7. And we had this, the value we had is this 0.659, which is your density. Okay. 0.659 is your density. So density is kg per liter, and we can write then we had as liter by kg per unit mass. So it will be 1 liter by 0.659 kg. Whereas for Cp, you determine the value of Cp from table B2. This is your N-hexane liquid state is only this liquid state 216.3. So 10 is to power minus 3 is in constant form. So it will be 68.74 minus 25. Now here in this first term, the second term will give us kilojoule per mole unit. But the second term will give us a very unique unit like bar liter per kg. So that will not work. So we have to do unit conversion by considering the value of R, universal gas constant. So we'll modify the first part here. Now, the molecular weight of N-hexane is 86.17 is the molecular weight. And we can use universal gas constants values. So basically, we have used two forms in R with two different units. With this, we can cancel out meter bar. We can also cancel it kg, and we will be left with kilojoule per mole. So if we solve this, we should get we should get delta HA as 9.38 kilojoule. So now this part is done. We already know delta HV is heat vaporization from the physical property table. Delta HV is 28.85. This one. Kilojoule per mole. Then we have to calculate delta H P, which is basically change in temperature from 68.74 to 50 degrees Celsius. And here Cp will be for N-hexane in vapor phase, so if you again go to the heat capacity table, vapor phase or gas phase, the Cp is this. To substitute these values again, the equation. This is your equation for simple. You have to integrate it then. To solve this by using a calculator. You should have 55, 59.54 kilojoule per mole. Right. Now, since we got all the values, all the change in enthalpy values, Q dot will be simply Q dot that we got is delta H dot. Now we are given a rate with 150 gram mole per hour into m dot into delta H hat. This m dot will be in gram mole per hour, and this will be in kilojoule per mole, gram mole. That means you should get the final answer in kilojoule per hour. So n dot is when 150 mole per hour. Delta H hat is basically the summation of all the enthalpies that we calculated. So it is 9.38 plus 28.85 plus 59.54. Get 97.77. Kg per hour. Now we can convert it to kilowatts easily. I just considering the fact that 1 hour has 3600 seconds. And 1 kilowatt is 1 kg/second. Just send it. Final answer should be close to 4.07 kilowatt. This is the final value of heat that must be supplied. That must be supplied. So with this, I'll end today's session. I hope you got enough practice for solving various kind of energy balance equations where it's problems where there was no phase change and some problem but there was a phase change. The next class we will continue with some more types of energy balance problems and cover the different aspects of the topic. Thank you guys for watching this video. Bye.